Hey everyone, today we are going to talk about the phi-4 interacting theory and the Yukawa theory if we have time. So in our last video, we talked about how we can add potential terms to the Lagrangian, and we talked about the theory that results by adding a potential term to the Lagrangian, and we call that a self-interacting term. Now we can actually consider specific potential terms, and one potential term that we can add onto is this term over here. And this term is what defines what we call the phi-4 interacting theory. You could use a different term. We could use like phi-3 or phi to the fifth, but it turns out that phi to the fifth, that would be non-renormalizable. We'll talk about what that means later on. And then phi to the third does not have an actual ground state, which we will also talk about later. And we divide this by 4 factorial because when we start doing Feynman diagrams, it's going to be useful to have that factor of 4 factorial down there. And by the way, like a factorial, that's just a times a minus 1 times a minus 2, and so on, just for review. So we can add whatever we want to the Lagrangian, right? And the particular thing we add will define different theories. So let's work with the phi-4 interacting theory and see what we get as a result. And something that I should add is that lambda over here, that is what is called the interaction coupling. And we add this coupling just to sort of like probe our theory of interactions. If we let lambda equal 0, then we just have a free theory. But as lambda approaches infinity, the coupling is larger, which means that this interaction term becomes more and more relevant, which means that the particles that it describes, once we start getting to scattering, will actually interact more and more. That's why it's very useful to define some coupling in that interaction term so that we can have some sort of sense of particles interacting stronger and stronger or weaker and weaker. And now we can apply everything from the last video into the phi-4 theory. So again, the Klein Gordon equation is going to be this over here for the interacting field, and we can just plug in what phi prime of phi is going to be. It's going to be this right over here, and this is going to be our interacting Klein Gordon equation. And then we know that our solution is going to be this over here, where g of x mu y mu, that's just the Green's function, which was the integral of e to the I k mu x mu minus y mu divided by k mu plus m squared. So here's our answer, right? But what is this going to be right over here? We need to know what that's going to be to actually solve this integral and find phi of x mu. Well, phi prime of phi, we saw that it's just this over here. This means that phi of x mu is going to be the integral of lambda. So basically, we can just integrate all of this together, and then we'd find out what phi of x mu is going to be. But the problem is that we have the thing that we're trying to find inside the integral. Assume that our field, phi, can be written in terms of a power series of lambda. So something like this right over here. So we can assume that it can be written as a power series. So that's going to be lambda to the 0th power, phi naught plus lambda to the first, phi 1, plus lambda to the second, phi 2, and so on, right? So that comes down to being phi naught plus lambda phi 1 plus lambda squared phi 2, and so on. Where phi naught, phi 1, and phi 2, and so on, these are just like sort of like elementary functions, right? That we're trying to superimpose together, assuming that we can write out phi in terms of a power series. This implies that lambda has to be significantly smaller than 1, or just anything smaller than 1, really. Because if lambda is bigger than 1, this means that each time we add by power of lambda, the series will get bigger and bigger, and it will diverge. So if we want phi to be convergent, which is really good, that puts a constraint on our coupling. It has to be less than 1. Because if it's less than 1, that means it can be written as 1 over a. And of course, like we'd have like phi naught plus 1 over a plus 1 over a squared, phi 2, and so on. And of course, this is going to be a smaller number compared with this over here. So that's why it has to be less than 1. So our series will converge to something. Well, then we can just plug in this ansatz right into here. We could alternatively plug this ansatz into our interacting Klein Gordon equation, into this, and and doing that we can solve for phi naught, phi 1, phi 2, and so on, right? Or alternatively, we can plug this into this over here and this over here, and it can give us solutions for each one of these. So by plugging in the series for phi in, and then by using the binomial cubed identity, this over here, and then by rearranging the powers of our coupling, we can arrive at this equation right over here. And we can just add up all of these things to get out what phi is going to be. However, we still need to solve for each one of these functions. And to do that, we can just match them to what's inside of here. So note that there's only one term in this series over here that contains a coupling raised to the first power. And there is only one term that contains a coupling raised to the second power, and only one term that contains the coupling raised to the third power. And note that this series is going to continue on, right? But we're going to look at just the first 4 terms and see what we get for each of them. So we know that phi naught is going to just equal phi naught, obviously. Now what's lambda phi 1 going to be? Well, lambda phi 1 is going to be equal to the term in the series over here that has a lambda next to it that's of the first power. It cannot be proportional to something that has a lambda squared or a lambda cubed in it, because then we wouldn't have a lambda in front. We'd have a lambda of a higher power. So this means that lambda phi 1 has to be lambda phi naught cubed. They cannot be equal to any one of these terms, since these are of higher order of lambda. Now what is lambda squared phi 2, the third term in our series, going to be? Well, that's going to be equal to 3 lambda squared phi naught squared phi 1 for the same reasons. And then for lambda cubed phi 3, that's going to be equal to 3 phi naught lambda cubed phi 1 squared. So we can see that if we know what phi naught is going to be, that'll give us what phi 1 is. If we know what phi 1 is going to be, that can give us what phi 2 is combined with phi naught, right? And if we know what phi 2 is, well, we don't need to know that for phi 3. But we can do the same thing for each one of the terms in our series. And if we know what phi naught is going to be, we can then just use this formula, this line of reasoning, to figure out what phi 1, phi 2, phi 3, and so on are going to be by this matching strategy that we've just developed right now. The question then becomes, what is phi naught going to be? Well, you guys probably guessed it. The phi of x mu was just phi naught plus lambda phi 1 plus lambda squared phi 2, and so on. If lambda is 0, we have a free field by the very construction of our Lagrangian, right? Which is over here, right? So if lambda is 0, we have a free field. So that means that if lambda is 0, phi is just equal to phi naught, which implies that phi naught is just the Klein Gordon solution to the Klein Gordon equation for a free field, right? So we can think of each term here giving us a correction term to our field. So think of it like this. So at the start, we have a field that is free, the free field. And then we turn interactions on. And when we turn interactions, we can approximate the full interacting field with this series. And as the interaction gets stronger and stronger, that means that each next term becomes more relevant. Or you can think about it as each term makes us get more precise about our field. So we can think of it as we're adding a small perturbation to our field, right? So here's like the phi naught plus lambda phi 1. And then phi naught plus lambda phi 1 plus phi lambda squared phi 2 gives us another small, slight perturbation in our field. And each higher term just changes our field just a tad bit, right? And it becomes like irrelevant as we add more and more terms, as long as lambda is, of course, less than 1. So that's why this series makes sense. We're trying to approximate the full interacting field with each small correcting term. It's just perturbation theory. We made a super small mistake. Recall that phi is equal to this, right? Which is equal to this over here. Note that there is an integral right over here, right? So this means that doing the same matching argument, right? We should be taking integrals of each of these terms. So like this right over here, just a super small change. So we do have to take an integral of this, and recall also multiply it by that Green's function at the end. We'd have to distribute that inside for each one of those terms, and we're just using gxy to abbreviate it to the Green's function. So yeah, we'd have to do that to actually find out where our full field is going to be. So basically this field is called interacting, right? Because we have these two fields at different space-time points. So think of it like this. We have one field at, say, space-time point x mu. One field is validated at y mu, okay? So you kind of have like two fields here. They're both scalar fields. And we're looking at them being evaluated at different space-time points. Basically, the field at the different space-time point will affect the field in the x mu space-time point, and vice versa. So the field that's right over here will affect the form of this field over here, and this form of this field over here will affect the form of this field over here. So the field is interacting with itself because they're also the same exact scalar field, just evaluated at different points. So in a bit more precise manner, we can kind of think of it like this. The field at this point, let me call this point like, I don't know, x equals 5, will affect the field at x equals minus 2. And that's encapsulated by this equation right over here. This, how the field acts, whether the field like kind of like jumps up and down or like plateaus off, how it behaves here will affect how it behaves here. Uses this equation right over here. And this Green's function is like the relationship that connects those two together, right? And that's why we call the field self-interacting, because how it behaves in one point will affect how it behaves in a different point. Whereas before, where phi of x mu, which is the sum of plane waves, right? How it behaved at like some points did not affect how it behaved at a different point, right? They're completely independent. You can think of them as like a bunch of springs together. Like you have a bunch of springs, how, like if this spring is like jumping like really high, that won't make this spring over here jump really high as well. But if our springs are connected with a string, then if this one goes up like really high, well then that will make this one go up really high as well, because they are all connected with that string, if that makes sense. So yeah, that's kind of how self-interactions work in our theory, and how the mathematics describes them in detail. So I don't really have much more time to talk about Yukawa interactions. I have to study for my AP exams. So we will talk about that in a future video. So thanks for watching and have a great day. Bye.